In this video, we're going to be talking about residence times for steady-state box models. And for this part of the course, we're going to be following the textbook by John Harte, and it's called Consider a Spherical Cow, a Course in Environmental Problem Solving. And in particular, we're going to be looking at Chapter 2 and Part A, which is about steady-state box models and residence times. If we have a compartment, we call that a box, and it could be, the compartment could be the human body, the body of an animal, a room, or a lake, an ocean, the whole atmosphere, or the whole earth. And what we care about is the flow in and the flow out of some substance. And if the flow in is equal to the flow out, then the amount of the substance in the compartment will not change, assuming there's no internal sinks or sources. So in other words, if the flow in sums over all the possible sources and the flow out all the possible sinks, when those are equal, then we say that the system is in equilibrium or in a steady state. And so if we think of a box, our compartment, and the amount of stuff in the box, we call that the stock, and we'll denote it by the letter M. So M is the stock, and it's the amount of the substance in the box. And then the flow in, that's the input rate. We'll denote that by F sub in, and the flow out is F sub out. And if flow in is equal to flow out, then the stock will not change. So if F in, so if F in is equal to F out, then we have a steady state. Or sometimes we'll say an equilibrium. And when that's the case, the amount of time the substance spends in the box can be estimated, or the mean amount of time is given by T, and that's equal to the stock divided by the flow in, or equivalently, the stock divided by the flow out, because the flow out is equal to the flow in. Now, if we have a non-steady case where the amount of the stock is changing with time, then this formula will not be right, and we would need a more sophisticated way to think about the residence time of material or substance in the box. All right, so as the first example, we're going to do the problem 1 in the book, and this one views a school as a box containing a substance being the students, and we're going to imagine that the school is in a steady state. So in other words, the rate at which new students are admitted to the school, the college, is the same as the rate at which the students graduate. So a college has a constant undergraduate enrollment of 14,000 students. So 14,000 is the stock, and no students flunk out or transfer from other colleges. And so the residence time of each student is 4 years. So it's a 4-year college. We know the residence time. And then what the question is how many students graduate each year. So let's set up this problem. M is the number of students. Enrolled. And M is equal to 14,000. And we have the admission of new students every year, so that's the flow in. And then we have the graduation rate, F out, is equal to the graduation rate. So this is a problem in which we know the residence time. It takes 4 years to graduate, and since no students flunk out and there's no transfers, then we know that every one of the students spends 4 years in the college. So if we use the residence time formula, T is equal to M divided by flow out, we can rearrange to get flow out is equal to m divided by t. And in this case, we know that m is 14,000 and t is 4 years. Graduation rate, the flow out, is 3,500 students. Per year. All right, so this is our first example of applying a box model in a very simple case where we know the total enrollment, we know the stock, and we know the residence time, which is 4 years. All right, for the second example, we look at problem 2 in the book. And the question is, what is the residence time of H2O in the Earth's atmosphere? So let's look at this one. So what is the residence time? So in this problem, the box will be the atmosphere. So this is the box. It's the atmosphere. And so the box is the atmosphere, and the stock M is the amount of water, or the mass of water, mass of H2O in the atmosphere. And so the flow in will be the evaporation rate, and then the flow out will be the precipitation. So to get a rough idea of what this number might be, the book suggests that if you think about the atmosphere, after a major rainstorm, the sky is pretty clear, and so you might think that there'll be a significant rain out after each storm, and so you might think that maybe a simple model for the moisture content of the atmosphere would be something like this. So you have some air parcel, and there's a gradual increase of moisture in the air until there's a rain event, and then it goes down to 0, and then it begins increasing again and then rains out. So T naught here would be the time between major rain events. This would be the time, and this is the moisture in the atmosphere. So this here would be up here, be the maximum stock of H2O. And so if the maximum is m naught and we think there's a kind of a linear increase and then a rain out where it falls out, then I guess the typical stock will be half as much as m naught, right? Because there's these valleys where there's less moisture, and then there's peaks where there's more. So if you average it, you could kind of think of cutting this triangle and filling it in here. And so that gives you a mean or an average amount of 1/2 m naught. And so then the residence time will be equal to m divided by the flow out, and the flow out is going to be m naught over t naught, right? So the amount that rains out, we have m naught, we go from m naught down to 0, and the amount of time between rain events is t naught. So f out, and that is equal to 1/2 m naught, that's m, and then the flow out is m naught divided by t naught. Right, so the flow out is equal to m naught divided by t naught. And so this gives us the residence time to be 1/2 of t naught. And so then to get the residence time, it's roughly a matter of estimating the amount of time between typical big rain events, which is about a week. So that would give us an estimate of about 4 days or so. Now, if we take the numbers, the textbook has an appendix and some numbers, and if we use those numbers, we will get a better estimate. In the book, they have the stock of water in the atmosphere is equal to precipitation rate, FW. For FW, you can calculate that from the maps you made in homework 1. You've integrated out the whole precipitation rate over the whole Earth, and so you could use that as the estimate. In the book, they give a number of 5.18 times 10 to the 14 meters cubed per year. And so then the residence time, TW, is 0.025 years, which corresponds to about 9.1 days. So it's not too bad from our previous estimate of 4 days. It's comparable. So for this problem, we want to look at the residence time of sulfur dioxide, the natural sulfur dioxide in the atmosphere. What's its residence time? And this is based on problem number 4 in the textbook. So the statement of the problem is natural sources add sulfur dioxide, SO2, to the atmosphere at a rate of 10 to the 8 tons of S per year, and that the background concentration of atmospheric sulfur dioxide measured in remote areas where anthropogenic sources are not likely to have much of an influence is about 0.2 parts per billion by volume, ppb. And the question is, what is the residence time of atmospheric SO2 in remote regions? So the fact that we can go to a remote area and measure the concentration of sulfur dioxide and expect that it will not be influenced by anthropogenic emissions suggests that the SO2 must not have a very long lifetime in the atmosphere. If it did, then the atmosphere would have time to transport and mix it throughout the atmosphere. As an example, in contrast, carbon dioxide, CO2, does have a very long lifetime, and so the emissions eventually get mixed throughout the atmosphere. And so it doesn't matter where you go in the atmosphere, you will see the influence of CO2 emission, anthropogenic CO2 emissions, on the concentration of CO2 in the atmosphere at any place in the atmosphere. And so we're expecting from this answer a relatively short lifetime, but the calculation will tell us roughly what it is. All right, so we're going to do it using a method of divide and conquer, which comes from the following book. And I really like this book. It's full of good strategies for solving problems or thinking quantitatively in science. He has another book called Street Fighting Mathematics, which is also quite good, which I recommend. Okay, so let's do this divide and conquer method. So we want to get the residence time, T, and that's going to be equal to the mass or the stock of sulfur dioxide in the atmosphere divided by the input rate, F. And so the divide and conquer, we're going to have to find both quantities, and we're going to use a tree and a hierarchical method to subdivide the problem. So let's go down this branch here. We need to know what the input rate of sulfur dioxide to the atmosphere, and this one is very easy. It's given to us. It's 10 to the 8 tons of S per year. And I'm going to convert everything to MKS units to make my life easier. So in the ton, there's 1,000 kilograms. So this becomes 10 to the 8 plus 3 is 10 to the 11 kilograms S per year. And now down the other branch, we'll need the total stock, so the total number of kilograms of sulfur in the atmosphere due to the natural emissions. So down this branch, we need M. And for this, we're not given the total mass of SO2. What we're given is the concentrations in ppv in remote regions. So I'm going to call that number the concentration F, which is in parts per billion by volume. And we know that the volume of a gas is proportional to the number of molecules. And so this number F is going to be the fraction of sulfur dioxide molecules in a parcel of air. So if we want to recover the total number of molecules, we would need to multiply this number by the total number of molecules of air in the atmosphere. So number of moles of air in atmosphere. And this will give us the total number of moles of SO2, but we're not quite done yet. This one is in kilograms, so we'd have to multiply this by the molecular weight or the molar weight of sulfur. So times the weight of sulfur per mole. And now we're going to go down this tree and find each of these quantities. So this one, sulfur is element has a molecular weight of 32. So MW is equal to 32 grams per mole, or 32 times 10 to the minus 3 kilograms per mole. And F, we already know, that's given in the statement of the problem. F is 0.2 ppv, so that's parts per billion, so 10 to the minus 9 moles of SO2 per mole of air. And we're left with the middle one, which is the number of moles of air in the atmosphere. This one would be equal to the mass, the total mass of the atmosphere, divided by the molecular weight, the mean molecular weight of air, And now we're going to subdivide this part again, so we'll need to know the mass of the atmosphere and the molecular weight of air. And air is composed of nitrogen gas, oxygen gas, and some other argon and other species, and it gives us an average of 28.96 grams per mole, or 28.96 kilograms, times 10 to the minus 3 kilograms per mole. And now we have to know what the mass of the atmosphere is. The book by Harte has an appendix, and it gives us the number, and it is 5.14 times 10 to the 18 kilograms. But if we didn't know this quantity, we can calculate it in the following way. So we know that the pressure at the surface of the Earth, P, is about 10 to the 5 pascals, which is 10 to the 5 newtons per meter squared. And we know that the pressure is due to the weight of the atmosphere above it. So if we take the total weight of the atmosphere, divide by the surface area of the Earth, we should get P. So we know that this is equal to G times the mass of the atmosphere divided by the total area, surface area of the Earth. And so we're going to use this formula. We're going to rearrange to get the mass of the atmosphere. So mass of the atmosphere is equal to P times the area divided by G. And so here if we didn't know this number, of course we can just use it, but if we didn't know it, we can set this equal to the pressure times the area divided by G. And then G is easy, that's 9.81 meters per second squared, or maybe better unit would be 9.81 newtons per kilogram. I think the latter units are more intuitive. It's it's the proportionality constant that gives us the force of gravity in newtons per unit mass. And then the area, for that we need to know that roughly the Earth is a sphere, so 4 pi r squared, where r is the radius of the Earth, and that's 6,371 times 10 to the 3 meters squared. That's the area, and then the pressure is 10 to the 5 newtons per meter squared. And if we combine these numbers together, we get a number, I think is 5.19 times 10 to the 18 kilograms, is what I calculated. And then we can work our way back up the tree. We take the mass of air and we divide by the molecular weight of air to get the number of moles of air. And for that, I got 1.8 times 10 to the 20 moles. And now if we multiply F by the number of moles and by 32 times 10 to the minus 3 kilograms per mole, we get the total stock mass of kilogram of sulfur dioxide, or sulfur in the atmosphere. Sorry, not sulfur dioxide, sulfur in the atmosphere. So this number becomes equal to 1.15 times 10 to the 6 tons, 10 to the 9, sorry, 9 kilograms of sulfur. And then up here, if we divide this one by the flux, we get equal to 1.15 times 10 to the 9 minus 11 is minus 2 years, which is equal to about 4 days, which is short compared to the mixing time of the atmosphere. So the original hypothesis that if we took measurements in remote parts of the atmosphere, it wouldn't be much influenced by anthropogenic emissions seems like a reasonable one. So our calculation is consistent, at least. Okay, so that was an example of using a divide and conquer hierarchical tree to kind of organize the calculations for a problem that's a little bit more involved. All right, the last problem we're going to do from this chapter is the one on anthropogenic sulfur dioxide emissions. So in the last problem, we looked at the natural emissions and calculated the residence time for sulfur dioxide in the atmosphere, and we got a number of around 4 days. And so that means that sulfur dioxide emissions will not be well mixed through the whole atmosphere because they leave the system before they have a chance to be transported over the whole globe. So the question in this particular problem is, with anthropogenic sources included, what is the globally average sulfur dioxide concentration in the atmosphere? So that's for the whole globe. And then what is the SO2 concentration in industrialized regions like the northeastern United States? And the way we're going to solve this problem, we're given the emissions for the global anthropogenic emissions in 1980 to be 8.5 times 10 to the 7 tons of sulfur per year. And we're going to assume first that this is well mixed through the whole atmosphere, and then scale the previous concentration of 0.2 ppb for the natural background concentration. We're going to scale that by the relative size of the anthropogenics compared to the natural emissions. And then we're going to apply the same kind of ideas again. We're going to scale those numbers to try to get a number that's representative of an industrialized part of the United States. Okay, so let's go through these calculations. So in the problem, we're given that 8.5 times 10 to the 7 tons of sulfur per year is the emissions. So F in is equal to 8.5 and that corresponds to 85% of the natural emissions, right? Remember, the natural emissions were 10 to the 8 tons, and this is only 8.5 times 10 to the 7, so that's 0.85 as much, or 85% of natural. So that means that if we want to get the well mix concentrations, we would take the concentration globally averaged to be equal to 1.85 times what we had for the remote regions, times 0.2 parts per billion by volume. And that corresponds to about 0.37 ppb. So in other words, we have an additional, so anthropogenic emissions contribute about 0.17. So anthropogenic emissions now, of course, this 0.17 of additional SO2 in the atmosphere is not going to be spread out uniformly through the whole atmosphere. So there will be regions close to the sources that are much more elevated, and places where we go far from the source where none of this emission will be present. And so what we need to do, what we should try to do, is calculate how much higher or lower, how much higher, I guess, would be the concentration close to the industrial regions. And for that, what we're going to do is we're going to scale this number by the proportion of the global emissions that are in the Northeast United States, which is an industrialized part of the world. And then we're going to also scale it by the fact that those emissions are going to be concentrated in a smaller volume of air. And so we're going to scale it by the relative size of the air shed for the northeastern United States compared to the whole planet. All right, so how do we do that? So we're told that F in for the northeastern US is equal to, I think, 10 to the 7 tons of S per year. And this corresponds to 12% of the anthropogenic emissions. Now, this 12% of the 0.17 ppb is going to be now concentrated in a smaller area. So we need to know what would be the size of the airshed where this extra flux is being put. And if we think of typical wind speed W to be about 15 kilometers per hour, and the residence time T is about 4 days, so 4 times 24 hours, then the distance D where the pollution can travel before it leaves the system is going to be W times T, and that turns out to be approximately 1,500 kilometers. So W times T of 1,500 kilometers. And so the picture they have in the book is kind of this one over here, where you have an air shed of 1,500 kilometers, and you have the power plants or the industrial sources of SO2 in the region, and most of the pollution doesn't get to leave the system. So some of it, of course, leaves, but there's some from the outside that comes in. And so kind of the typical volume or area representative of where that pollution resides is given by this calculation here, by this distance for the size of the airshed. And so that means that these emissions, which are 12% of the global, are going to be concentrated in a smaller volume of air. And so we should scale up our concentration by the smaller volume. And so that means that this concentration in the northeast US is going to be equal. So this is how we'll do it. So it's going to be 0.17 ppe. And then we scale it down 0.12%, 12% or 0.12, because not all the emissions of the globally, which only 12% are in the northeast US. But then we have to scale it up because the emission, which are less, are concentrated now over a smaller volume. And so for that, we'll take it to be 1,500 squared relative to the total area of the Earth. So if we take the area of the northeast US to be roughly equal to d squared, so that's 1.5 times 10 to the 6 meters squared, and we compared, sorry, not 1.5, this is all squared. And we compare that to the total area of the Earth, so the area of the Earth is 4 pi times 6371 times 10 to the 3 meters, all squared. And so we can take the ratio of these two, A northeast over area of the Earth is equal to, let's compute that. Alright, so the radius of the Earth, 6371 meters, and the area of the Earth is 4 times pi times A squared, and the area of the northeast US, let's take that to be d squared, the fraction covered by the northeast US is A northeast divided by A Earth. I think in the book they use a number of about 0.002, so 0.0044, which is about 4% of the Earth area. And in the book, the number they have, they say that it occupies about 0.2% of the Earth's area. And so we should scale this number up by 0.002, right? 0.2%. So I'm going to use the book's number. Book 0.002. It's a rough number, and that corresponds to, I think, about 10.2 ppb by volume. And to that, I guess we can add plus 0.2 for the natural background, so that would make it 0.4. 10.4. But I mean, this is negligible compared to the errors we're making in this rough calculation. Alright, so the reason I did this problem is not so much because I'm an expert on sulfur dioxide. In fact, I know very little about the chemistry of sulfur dioxide or atmospheric chemistry in general. If you're interested in these issues about the sulfur cycle, you can talk to Professor Saltzman, who is an expert on the sulfur cycle. But the reason that I wanted to talk about it is because I have a personal connection or experience with sulfur emissions. So the city in which I grew up is a mining town in Canada called Sudbury, Ontario. And in preparing for this class, I looked up for some articles, and I found let me see, where is it? Yeah, over here. So this is a picture of Sudbury, Ontario, where I grew up in, and these are the tailing ponds, so it looks beautiful and a horror at the same time. And here's another one showing the slag from the smelting operation. And here's some beautiful yet horrible pictures of the tailings. So this is the leftover from the smelting operations, which incidentally would release a lot of sulfur dioxide to the atmosphere. And so most of these emissions were, the slags are the byproduct after they've extracted the nickel, but another byproduct is something they would spew into the atmosphere in this giant smokestack. So when it was built, it was the tallest structure in Canada, and it was the largest point source of sulfur dioxide in the world. And I guess at the time when it was built in the early to mid 70s, I guess the solution to pollution was dilution, and so the idea was to put the pollution high up in the atmosphere and then dilute it by spreading it downstream. And so that helped ameliorate the air quality in the local area, but produce acid rain problems downstream. Since then, they started cleaning up the operations, and now the smokestack is no longer being used. In fact, they've built some smaller ones now, and there's much less SO2 emissions coming out of these smaller stacks, so they've have much better technology to help clean up the air pollution. And by not using the giant one, the stack was so big in the end that you would have to burn extra natural gas, more than you needed to do the smelting, just so you can create enough of an updraft to get the smoke to go all the way up the stack and then emit out the top. And so this article in this Christian Science Monitor magazine that came out in September points out that by shutting down the oil stack, the emissions of CO2, not SO2, from the burning of the natural gas to run the smelter is going to decrease by 50%, which is a good thing. One thing that was interesting and made me laugh when I was reading this article is, let me find the quote. Yeah, here it is. Okay. So this is a little bit of a sad quote. So it says here, I'll just read it. Dr. Gunn, director of the Vale Living with Lake Center in Sudbury, recalls attending his first international science conference in Ithaca, New York in 1980, and learning that his peers were using the name Sudbury as a unit of pollution. And this is how it would be used. How many Sudburys does your country represent? He says he has since devoted his entire career to make the term Sudbury known as a unit of restoration instead of a unit of pollution. So how many Sudburys? I don't think the name has caught on, but Sudbury would be an amount of SO2 emissions. But now, I'll show you some pictures down here. So this lake, this picture is Silver Lake, which is close to Sudbury. Used to be one of the most polluted lakes in the world with lots of heavy metals and very acidic, but it's been since been cleaned, and now it's possible for people to swim in the lake. And so there's been a lot of work to try to clean up the SO2 emissions from the smelting operations. Of course, nowadays, and also at the time, I guess, most of the emissions are due to the burning of coal in power plants. And so I also downloaded some data to see how different the numbers might be compared to the ones in the textbook. So the book has numbers from 1980, which is when, I guess, 1988 is when the edition I have. Yeah, the edition I have is for 1988. And almost all the data is from the 1980s. I think there's some that are later from 2012. Not for the SO2, but for other problems. I'm not sure how it is that a book that has a copyright of 1988 has some tables that correspond to 2012. But in any event, so I've looked up, to get back on track here, what the SO2 emissions are today. And so I downloaded some data. So let me show you the data. Right, so I downloaded some data from the Socioeconomic Data and Application Center, CDAC, and I've gotten data for the SO2 emissions from 1850 to 2005. I didn't find any data beyond 2005, so I don't have the most up-to-date data. However, I'll show you what I found. So the spreadsheet has emissions by country and the total of all countries from the period of 1850 to 2005. And I made the following plot from this data. If I can find it. I made this plot over here. The top one is the total anthropogenic emissions in tons of S per year. So the total, I guess, is the top one. Is that green or blue? The blue curve, the light blue curve, is the total. And here we see that in 1980, the emissions are about 6.5 times 10 to the 7, whereas in the number we had from the textbook was about 8.5 times 10 to the 7. So it seems like the numbers have been revised downward since the time the book was published. The other curves I have, the dark blue one over here, these are the US emissions, which seems to have peaked in the 70s and have been decreasing ever since. So cleaner technology, I presume, all the way to 2005. So the US SO2 emissions have been decreasing, whereas the red one is the emissions from China, which have been going up fairly rapidly and surpassed the US in probably the early 90s. And then the green one is the one for India, which is low relative to the US and China. But I think I've read somewhere that the most recent emissions, India emits more than China. So I think the Chinese emissions have started to decrease, probably because of their attempts to mitigate air quality problems. But in the developing world, where they've been building more power plants, their emissions have been going up. And then for comparison, I put the tons of emissions per year from Canada due to smelting alone. So that's not all the emissions. So you notice here this is times 10 to the 5, and this one is 10 to the 7. But this is for smelting only and for Canada only. And the reason I put this one is because I presume that in the 1960s and 70s, almost all of these emissions are due to the Sudbury emissions, which accounted for almost 4% of the global emissions. Global anthropogenic emissions were due to the smelting operations in Sudbury. And since then, since the 70s, they were, so there's been a decline, and that's because of cleaner technology to try to limit the amount of SO2 emissions. All right, so I'll go back to here and leave you with the photographs from Ed. Let me get it. Ed Bertinsky is the photographer and filmmaker who took these pictures of the slags in the tailings.